in that approach. Now, this is a slide that you've seen before. It's unchanged. This talks about how Gray's hash join works. I hope everybody remembers the general idea of what that works, how that works. Just as a very fast reminder, I have, assuming I have three main buffers, I have a hash function h, and in the build phase, what I'm going to do is I'm going to build partitions of R and S, the two tables that I'm joining, using this hash function h. And I know that I'm going to build those based on the join column of R for R, the join column of S for S. And so I'm going to put those things inside partitions. So I'm going to build, for example, partition R17 and partition S17. And as we've emphasized when we talked about Gray's hash join before, if there's a match between something in R17, it's got to be in S17. Because if a hash based on the same value, it's got to have the same value. I mean, I'm using the hash, the join column of R and the join column of S. So, basically I end up creating however many, B-1 in this case, different hash values that I'm playing with. And now I have a variation of the original problem, except now I have to join R17 and R17, as well as R1 and S1, R2 and S2, R100 and S100, R101 and S101. That's what's going on there. So in the build phase, I build the partitions and I've reduced the problem to the same problem, but with a smaller amount of data. And if I'm lucky and good, then things end up fitting pretty much inside memory. The thing that I do inside the next phase is I see what I can do about putting in a part of R inside memory. Maybe all of R sub 17 fits inside memory, that would be nice. But I can fit a part of R inside memory, and then one by one, with this approach, I'm going to be going through what might be pretty big buffers of S, and I'll look for the matches. And when I build that hash table inside memory for R17, I'm going to use a hash function. Do I use H again? Remember about the definition of insanity, which is doing the same thing again and expecting a different result? Everything in R17, H of all those tuples was 17. That's why it's R17. So I pick another function, H2, which is very different from H. I have a wonderful class of universal hash functions that I use. And so I'm trying to do the join between all the S tuples and the segment of R that I have inside memory. And maybe everything fits inside memory, which is nice. If not, I'm going to have to do this again, going through each of these segments that I have of R sub 17, basically B-1 blocks at a time, putting them in a hash table in memory. Yes, a hash table takes a little bit more than the actual data pages, but not much. And as I get things that are coming out, I put them into my output, and yes, I pretty much want to have shadow buffers so I don't have to delay while I go out and read things and all the rest of it. And I will recall, I'm not going to put up the slide on this, remember that if need be, if these things end up being big, I can recursively apply the same algorithm yet again, and go ahead and combine these things and use the same trick again with a different hash function to be able to recursively be able to combine these things together. So that was the algorithm we talked about. So in build, I'm creating this R17 and S17, where again I know things in R17 can only match things in S17, and I do this, for however many values of the hash function I have. And then I'm going to read in a partition of R. With any luck, it fits inside memory. If things are too darn big inside R, maybe I switch the roles of R and S if S is small, right? Or maybe I go ahead and recursively repartition to be able to do this. And then I find the matches and I have them go out. Well, the whole point of this is that this is a wonderful algorithm for parallelism in both the build and the matching phase. So basically what I end up doing is I can go ahead and in parallel, I can do my build. What I'm going to do is I'm going to break up my data. If suppose that, for example, R and S were partitioned. In other words, R is stored in 100 different places. S is stored in 75 different places. I can do my creation of R, R sub 17, S sub 17, R sub I, and S sub I for all the different values of I. I can do this in parallel. Bringing in data from all these different places and creating the data, the R17 and the S17. There's no reason why I have to bring all the data together to do this. And there's no reason why I have to wait until I take my first partition of R and have it handled before I go to my second partition of R. I can do this in parallel. In fact, suppose that R wasn't partitioned. Suppose that there were something where, R had, 100 million tuples in it, but they were all at one place. Kind of dumb to do, but maybe I've done that. That's how my file got created. I've got a whole bunch of cores. I've got a lot of memory. I can stick my finger in. I'll just make it easy. I'm going to go worse than that, but I'm going to make it easy. I'm going to stick my finger into 100 different places inside my 100 million tuples of R. Starting at tuple 1, starting at tuple 1,000,001, 2,000,001, 3,000,001, all the way up to 99,000,001, 99 million bottles of tuples on the wall. And I have 100 different places where I start doing the processing of the file, using different cores and memories to be able to do it. I can operate in parallel even if the data wasn't partitioned. So, lots of parallelism, lots of different things. So I will have a place, a whole bunch of different places handling partition I. So there'll be a place 17, whatever that place is, that I send the data that goes into R17 and the data that goes into S17. And again, suppose that I have, 503 different things for my partition. I'll have 503 different places where I send the data. So in parallel, I'm creating the partitions, the R17, the S17, the R502 and S502, etc. And I'm sending them to these other places, which is getting the data. And I can operate when the partitions, when I have all that data existing, for dealing with a match phase, I can do my thing for H2, right, for the match phase. I can do this in parallel at all these 502, 503 different places that I have. In fact, I can even start doing some of the matching before the entire set of data has arrived. So there's a huge amount of stuff that I can end up doing. So the actual match part to complete the join is done in parallel. There's no reason why this has to be done as a monolith. It gets split naturally into a huge amount of parallelism. Parallelism in the build phase, taking different pieces of RNS and finding the things that go to each of the locations in parallel. And parallelism in the match phase, because again, at each of these different partition sites, I can do the matching on independent of the other things, and I produce the results, and that's my answer. And by the way, my answers have been created at a whole bunch of different sites, which may make it easier for me to do whatever the next stage in the pipeline is based on that, because my answers are at different sites. Take advantage of that if you're pipelining as you go. There is one minor issue with Grace hash join, which is that unlike what we've seen with index nested loop join, which you should remember since it was on the midterm, you have to look at every tuple in both R and S. Now it could be that only a few tuples inside S participate in the join. Why would that be? You have all the things on R and only a certain number of sailors reserve boats, or whatever it is. Not all the sailors reserve boats. Right? So it could be that R is looking at reservations, let's say, that were made on Wednesday, or whatever it is. And for some other reserve, you don't have to look at all the different sailors. No, the sailors table isn't all that big, but let's take the case in which you're looking only at some set of sailors, and you don't really have to look at all the reservations to be able to go ahead and do this. There are, again, various things that you can play on this. But Grace hash join, whatever the RNS is that you're joining, you have to deal with everything in R and everything in S. That's the way it works. If there are very few tuples inside one of the tables, there are clever things that you can do. There are times when index nested loop is better. And it's better when you only have to do the index lookup for a relatively few number of tuples. You don't have to scan everything. If I only have to look at 100 things in my index nested loop join, it's going to be better to do that than to do either the merge join or the hash join. the question is, how do we take INL in next nested loop join and fit it into the parallel world? And the idea is you take the small relation. Suppose one of the relations is small compared to the other. So I have a situation in which R is small and S is big, unlike the cellular example. And suppose I have a situation in which S is scattered across, again, 50 different places. I haven't hashed it, it's just the way it ends up being stored. S is stored in 50 different places. I store things in different places to get great parallelism. So the S is stored in 50 different places. R is dinky. Still might be, a megabyte, but these days a meg is pretty small. R is small. I send R to all the different places that have S tuples. All of R. There are games I can play, but we're keeping it simple. Send R to all the places that have S tuples. And now I do an index nested loop join between R and the values of S that I have at these 50 different places. And because R is small, sending it out to all these different places as a broadcast is not a big deal. So I can join that entire outer relation with the partitions that I have at these 50 different places. And I can use a next nested loop join to do that, and that's potentially going to be better. So should the outer relation be the bigger one or the smaller one? The outer one should be the smaller one, because you're broadcasting it to all the places. You don't want to broadcast the big one. Now we get to parallel sorting. Okay, and we're going to talk about how the things end up going. There are lots of different ways of doing parallel sorting. We're just talking about the simplest variation. So what you can do is you can scan in parallel doing range partitioning. And again, I'm going to make it simple. Suppose that I have something in which I have names. And again, I'm going to be dumb about this just because I want to keep it simple. I'm going to take all the names that start with A and send them to one site. I'm going to take all the names that begin with B. Right? They're not already, partitioned by name. Maybe they're partitioned by something different, like social security number. So I end up taking all the things that start with A and I send them to one place, and all the things that start with B and I send them to another place, and so on through C through Z. And yeah, I know that letters aren't uniform. It's just a simple example to show you how you do it. We'll talk about that uniformity issue in a second. And then as the tuples arrive, I'm going to sort them locally. And in this case, I just split it into 26 places, but maybe I take the first two letters in the name, and so I've got 26 squared, which is something like 576, I forget. And so I sent it to 500 and change different places. Or maybe I break it up into 100 different places, or whatever the number of things is. And then I have 1/100th if I sent it to 100 places of the original tuples. And so sorting that is going to end up being faster. So I get, and I can do it in parallel in these different places. Because all the A's come before all the B's, come before all the C's, come before all the D's, et cetera, et cetera. So I've got the thing spread across the system, and it's sorted, and and again, I have something partitioned that may help me with the next part of the query that I want to execute. And isn't that neat? There is just one potential problem, which I've already alluded to. Skew. Because more names start with S than start with Q. And so if I do the partitioning based on something where things are very non-uniform, I'd like to have all the pieces be approximate. They don't have to be exactly the same. I'd like them to be close to being the same. If one is twice the size of another, may not be a big deal. If one is a million times the size of another, that might be important. If one is a million times the size of every other piece, yeah, that's a problem. I'm not getting benefit from doing this partitioning. So one solution is sample the data. Try to find, not touching that much data, try to find a good way of breaking the thing up. You make an assumption if you're doing random samples, or maybe even multiple random samples, that something that would range partition a sample where I only look at, let's say, 5,000 tuples. I figure out a good way of uniformly partitioning the 5,000 tuples into 100 pieces, which I will assume, and often, but not always it will be the case, will be a good way of partitioning all my 100 million tuples. So that can work. How many of you have heard of MapReduce? Good. What you're going to see is essentially MapReduce, but it was done in parallel database well before, which actually caused a little bit of animosity between Mike Stonebreaker and David DeWitt. on the database side, and the people, Jeff Dean and Gamelot, who wrote the MapReduce paper. And in fact, there are lots of similarities, but there are also differences there. So, for each aggregate function, you need to be able to do a decomposition, and everything is really easy to partition for certain functions. If you want to count, then if you have 100 different pieces, you want to count how many things there are, how many people are there whose salary is more than 10,000. If you count the number of people who make more than 10,000 in each of your 500 pieces and then add that up, you get your answer. So you can operate across 500 different pieces. And as again I've emphasized, you can have the 500 different pieces stored in 500 different places, or I could stick my finger into, even if it's stored in one place, in 500 different places, and take advantage of multiple cores and so on to be able to add things up. If I want the average, it's very easy to add up sum. It's very easy to get the count in parallel. Count divided by the sum of the counts divided by the sum of the count, the sum of add up the sums, the sum of the sums. Sum of the sums divided by the sum of the counts gives me the average. So that's all there, and so on. Minimum is easy, maximum is easy. Some things are a little more complicated. So basically what I can do is I can sub-aggregate the groups close to where the data is, so I don't have to send the data around. Maybe I can do it where the data is. And then, I can pass each of the sub-aggregates to the site that corresponds to, a group's partition site. So what I can do is I can go ahead and do the aggregation even. Well, the aggregation's pretty cheap, but I can do the aggregations in parallel too. So for example, just as a very simple example, I could go ahead, suppose I have all my stores in the North region, South region, East and West region. I can get the values, things like the sum and the count, for everything in each of those 4 regions in parallel, and then I can combine those together further to get the sum for everybody. And it didn't have to be 4 regions, it could have been 100 regions or something like that. So this is pretty similar, if you know about MapReduce, to how combiners work. In terms of that, I can end up getting results for groups of things together and then combine the results of the groups in various ways to get an answer. Okay, as we end up going through, drinking my coffee. If you have a query plan and you have a situation in which you want to be able to end up putting things together, you can pipeline between the operators. So in particular, if what I want to be able to do is be able to join, and I've got this bushy thing, which system origin support, but current optimizers and executors all do support. I want to take the join of A and B, I want to take the join of RNS, I want to go ahead and then join those results together to produce a result. Maybe, and this is a far smaller number than you would probably use, I can go ahead and join in parallel between A and B at 4 of my sites, or 4 cores. And I can do the join of RNS at 4 places, then I take advantage to all 8 places, maybe to be able to do the join, to be able to put the result together. So that ends up being kind of nice, but recognize that depending on what I'm doing, there are blockages in the pipeline. There are times when the pipeline gets constipated and things can't flow through. An example of that is if I'm trying to do an aggregation, I don't know what the aggregation is until I have all of my tuples, or at least all of the values for one particular range of partition. If assuming that I have a group by, the group by thing might say, well, if I have the result for this group, then I'm done with that group, but I can't get finished until I have everything in the group, all the values that end up coming in. Doing a sort, I don't know the result of the sort. I'm getting the results in a given order. Maybe because I'm doing sort merge, maybe because I have an order by. I don't have my result until everything is there. It blocks the pipeline. And also the build phase that I have in hash join, that blocks the pipeline too, until I have the full result of the partition. I can get a partial answer, but I can't get the full answer until I have the entire partition. So there are lots of different things that can end up blocking the pipeline, and I've given you some of the examples of that. But again, one of the reasons why bushy trees are very much in is that I can take advantage of parallelism as a way of doing the A join B and the R join S in parallelism. So I can have parallelism within the A join B, parallelism in the R join S, and but I can also be doing the A join B and the R join S in parallel with each other. And then as I get results, depending on the join algorithm, I may be able to join results as they come together. So it's very easy, which means it's a simple matter of programming. Everybody hear the phrase SMOP? What that means is, the idea is simple. Programming it to work well can be a lot harder. You know, conceptually, it's easy to describe what the algorithm does. Heck, we just spent the entire lecture talking about a big part. There's a lot more of what's involved in parallelism. Actually programming the thing to be able to work well, dealing with what's in memory and how many cores you have and how you deal with the network well, and you know, whether you're polar push and how much parallelism to have and all the rest of that, that's fun. That's the easy part. You know what the hard part is? My friend, the optimizer. So when I say that this is easy, I don't mean it's easy. I mean, we're talking about, you know, Aleph nil versus Aleph 2. I mean, orders of infinities. Dealing with this and implementing it well, that's a lot of work. I mean, it's much more complicated than we've gone into here. But the optimizing of it is much, 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 much harder because there are so many different choices to make. If you could examine each different choice, you'd still have a pain because your statistics are not quite right, your cost formulas are bogus, and all the rest of that, and there are always, you know, how much parallelism do you have, and which things do you know, what resources do you throw at which part, and what happens when you're wrong, and how can you use learning these days to be able to make it better? I mean, there are just so many choices to make, and figuring out good heuristics to do it. Remember, the goal of the optimizer used to be to avoid a terrible plan. These days, it's to find a pretty good plan, and the queries are so darn complex. And being declarative has the disadvantage that there are so many different choices you can make. Free will is an advantage and a disadvantage. You gotta make decisions. And it can be rough sometimes. So here's a common approach, which I will explain, but I will tell you it's not always used because it doesn't always work. And I'll show you why. Basically, you go ahead and first find the best sequential plan, e.g. using a system R or something more modern. You find the simple plan, then you figure out how much parallelism to have. Seems like an easy way of breaking down the problem so it's finite. If it worked, it's got problems with it. So basically, you go ahead and you decorate the query plan with, you know, this is going to these 5 sites, this is going to those 3 sites, you know, this is staying locally, this is going even more remotely. Here is the problem, and this is about pretty close to being done with this, but not quite. The best serial plan is not necessarily the best parallel plan. Why? Here's a trivial counterexample. We've got 2 sites. We've got the data A through M at one site, which, you know, site 1. We've got the data N through Z at site 2, okay? And basically, we have a range query, such as the one that's situated over here. We've got a telephone book, A through M and through Z, and we want to get everybody from the telephone book where the name is less than, quote, no good, because this is a no good plan. Now, if we were taking a single plan and decorating it with a parallelism, there are 2 approaches that you might use. One is to do a sequential scan, and the other is to use an index that you have on name. You know what? For site 1, sequential scan is a great thing, A through M, because you don't have to touch all the data, because all the data is less than no good. What about for site 2? Less than 1% of the data, assume. Because that's N through Z. Less than 1% of the data is going to be less than no good. So for that site, using your index would be a better way of doing it. If the way we're doing it is taking a serial plan and decorating it with a degree of parallelism, either we're using scan, table scan, file scan, or we're going ahead and we're using the index. One of the approaches is better for the first site, and the other approach is better for the second site. So whatever thing we're picking is suboptimal. It would be better to use one approach on the first site and another approach on the second site. And this is a really simple query. It's much, much worse than that. And I have 2 minutes. I will begin next time by going over this slide again, as well as my summary slides on this, and then we'll get into distribution. So we got a little bit further than I expected, which is good. The amount of parallelism that exists at all sorts of different levels is huge. And this is a description. I worked at SAP before I started teaching here. And SAP HANA is a relatively modern database system that's particularly good on dealing with OLAP. Let's talk about the parallelism that exists. There are multiple users who are doing different queries. Lots of parallelism there. There are lots of concurrent operations that you can do inside a query, as we've talked about, where things can be done where they're independent of each other, things can be done with pipelining, all of that stuff exists. You have data which gets partitioned across a whole bunch of different systems/cores. Data can be partitioned across a whole bunch of different systems, so that thinks that it works. Okay? You can also, by the way, as I mentioned before, even when the data is in partition, you can stick your finger into 100 different places. Right? Even when the data is partitioned, you can have different cores operating on different segments of the data, even when it's not partitioned, and take advantage of parallelism for that. Okay, so you can go ahead and using that kind of idea, you can do concurrent aggregation or concurrent scanning, either when there are 100 different places or sticking your finger into 100 different places. Intel hardware does multi-threading. Those of you who have taken hardware courses have seen how that ends up working, to be able to have different things that are going down you have a whole bunch of different cores that are going on, and Intel can do a whole bunch of other stuff in parallel for you in terms of sequential prefetch. But the most interesting one of all, and which is surprising to people, is vector processing. The scan that SAP does, and it's not just SAP, it's everybody, operates at faster than clock speed. Huh? How do you do operations that are faster in clock speed? Well, let us suppose that we have an encoding of values where it's, let's say, 6 bits. Our word is 32 bits, and our encoding of the values is 6 bits. Thus we have, 64 or fewer different values, so we've encoded them using 6 bits to the 6 to 64. Last time I looked, probably hasn't changed. What you can do is you're scanning looking for a value with Intel vector hardware. You can look, a word has 32, which is 5 1/3 different values inside it. I can do the scan looking for the value that I'm trying to match. Intel hardware, without my having to program it, will do that search for me, writing the instructions properly. In parallel, doing vector processing to do, well, the obvious is to say, well, I can do 5 operations in parallel, and that will do it. It's actually better. It will do 5 1/3 operations in parallel. As long as it fits in a cache line, I will be able to do 5 1/3, meaning I've done part of the next comparison. I don't waste the extra 2 bits. I can have things jammed together where I have 5 1/3 things in my 32-bit word, and it will do the processing with respect to that. So there's parallelism that exists at that level as well, which people like and want to take advantage of. It's one of the reasons Intel put in the capability to do it, because database is big, and data management in general, because it's not just for database. It's big business for Intel and everybody else. So there are about 7 different layers here where there's parallelism going on. Whether it's database or other data management, it's huge. Huge! I'll go over this quickly again and go over the summary next time, and then we start on distributed data.